Okay, and we're live. Welcome. This is, I guess, part 3 or part 4 of the NEStonia build challenge. We're at 61 parts. Today we're going to place 13. We're going to start placing some interesting parts now. We've put all the boring parts on the board, and now we're going to have a little bit of fun with some actual active parts. We're looking at some Schottky diodes. We're looking at some PNP transistors. We're looking at some MOSFETs. We're looking at a crystal and some MEMS microphones. If you're catching the stream later, or catching it live right now, thank you for tuning in. Let me just check the chat real quick and see. I guess I'm gonna kill that desktop audio now. That's we're done with that. All right, so I think we're just gonna jump right into it then. All right, let's see what we got here. Q456. We'll start with those. How is everyone doing at home? All right, let's find where these guys live. Q4. All right. I think it's called SOT363. They're pretty small. Either that or it's like basically a T-SOP, something like it. All right, let's take a look at what it is. So what is Q456? MMBT 7002, etc. MOSFET 2N channel, 60 volts, 0.3 amps, SOT363. So if we take a look at our DigiKey stock, Q4 is 6. What is it? Oh, we passed it. All right, so here's our Q4 to 6. 2,869 that DigiKey has. Q456 on Mouser. 5,776. So pretty competitive. But anyways, we want to actually see the part, so let's pull up some data sheets here. So, pretty standard stuff. It's a twin MOSFET, twin N-channel MOSFET. That's all there is to it. Anyway, let's find that guy in the schematic. So basically, the micro has a pin coming off the GPIO when it wants to turn itself off. We could take a look at that. Suicide is on PD2, which is the only GPIO pin on the D port, so this prevents accidents from happening as far as software is written. Having it on its own port and nothing else. It's just a little bit of security, because the micro cannot turn itself back on. Once this pin is loaded and it hits the MOSFET, it basically shuts the power control flip-flop off, because it's connected to the clear. Anyway, I'm going to shut up about that and start doing some soldering. All right. So where was that again? It's on the back. Okay. So, folks, you were wondering maybe I went away or something. What happened was I streamed 2 4-hour streams back to back, and nobody showed up to view. And I just figured, well, I did 61 parts, and there's only 163 to go in the completion. So I figured it was time to take a little break. And there's our Q4. Let's get our scope. I think the focus is pretty good. I think we could... I guess that's good. All right. These parts do have some orientation. And you'll see that there's one arrow on the board, so you got these 2 lines on the silk screen. And this one's a little longer. That's your pin 1 right there. And there'll be some kind of indication on the chip that where pin 1 is. Gotta flip that guy over. A little more challenging now because there's no okay, so we're gonna have to get a little bit closer here because I can't see what the hell it says there. So I guess it doesn't matter which is pin 1, right? Because the way the chip is designed, you can put it... Let's hold on. Let's go back to the schematic there. Six and 3 are drains. 1 and 4 are sources. Which kind of seems to mean that actually the orientation doesn't matter. I might be wrong. But it seems to me if you rotate this 180 degrees, you get the same thing. So therefore... explains why it's hard to determine the orientation. So we're just going to charge forward and, you know, whatever orientation we got there, it's probably going to work out. Anyway, so hopefully people will show up in the chat and yell at me and tell me I'm doing it wrong. Or not. But... okay, let's get back to this. Yes, that's good. Excellent. So I guess the way we got to do this is we're going to blast one side with some solder. Okay, so that sucked. Gonna be a hard one, folks. I'm not fooling around, folks. We're using flux like nuts. Now, the way this usually works is you can usually just tip your iron and then just go in there. I've seen that work. I might have just had too much solder on my tip. We're going to clean that up because, you know, it looks like hell. Holy smokes, this is going to be a long stream. It's only 13 parts, but look how hard that is, man. I'll get back to that printer right away. I'm in the middle of something here. It does look like it's bridged. It looks like it's bridged. We could probably just wick it though. I think we're going to call that a pass, but we're going to touch up the other side. Okay, we're just going to pause for a microsecond. I'm going to get the printer all going again. It's really easy to misjudge how much solder you need to use when you're doing surface mount, especially this stuff. It looks big on the camera. And then when you go and touch it with the solder wick, you have to wipe the tip of your iron every time. Otherwise, you're gonna waste your time with the wick. I think we're good with that one. But let's take a closer pick. Whoops. I mean, I don't know. I think we gotta move on. It doesn't look like there's a cold solder joint. It's really hard to tell, you know. There's no... It's really... The depth perception is just really hard to tell under the microscope, so... Without, like, a side view or something, it's very... But, you know what? We're just gonna say that looks good. So there you go. And... Yeah! Whoops, that came a little out a little hot. Anyways. Alright, Q5. What is this? Oh, it's just right next to it. Okay. Make that a little bigger. Yeah, we've already gone through this. Sorry, folks. I'm just first day back at work again. You know. Maybe I'm just procrastinating, right? Because it's just it's just go now. Q5's right there. All right. I guess we'll get that part picked now. Well, that was a bit of luck, folks. It landed on its feet. thought it landed on its feet, but I guess it just looked that way on the scope. Well, we got a solder bridge there, but we'll get back to that. It's a little crooked, which really means it's going to be a little bit of a challenge. So we had a solder bridge, and then it just disappeared. I like that. Well, it's just some gunk there. It's bugging me. Okay, we're almost done. Just gotta fix that guy. Oh, that happens. That happens. You see, folks, that's why we're only trying to do 13 parts. Guess I'm not having a lucky day here. Let's see what's going on in the chat. See if there's anything going on there. Nobody's watching. We gotta use those other ones. It's that capacitor. It's in the way. What a hard one. I think so. Yeah. All right, Q6. All right. So that's on the back side as well, close to the right USB port. I'm starting to get with the program, folks. We're not doing that. Q6. I didn't talk about Q5. I guess we can talk about that. So Q5, that's Q5B, and Q5A. So the way this works is these go to the microcontroller as in open drain output. And the reason is because of when the microcontroller powers down, needs to be isolated from the input. So we just use a MOSFET to do that. So the sink means that the right USB port, or left USB port, is it left? Yeah. The left USB port is a sink, which means that it requires power delivery. And so that's all that indicates. Rather than it being, say, like a source of power, where NEStonia is the sink. And this MOSFET, Q6, so that's Q5A. Q5B is VBusL, so if you actually do have a power source, if NEStonia is a sink, then VBusL will be active, pulled low. Same deal as sink L. It uses the microcontroller's internal pull-ups to pull the signal, so we don't have any external resistors. And then Q6, it's just for the CC lines on this, since the port itself has to switch roles between source and sink. When NEStonia operates as a sink, the Q6 MOSFETs are engaged, which pulls the CC lines to ground through 5.1 k ohm resistors, as you see on the other side, which is always intended to be a sink. NEStonia, that is. And yeah, and then when NEStonia is a source, then these MOSFETs switch off and the 5.1 Ks are effectively removed from the circuit. Anyway, enough about that bullshit, and let's get back to our microscope inspection placement. All right. With these really small parts, I guess the thermal relief is kind of important. Maybe I could have been more thoughtful about that. Well, I guess we gotta wet the pads. Nice cleanup, by the way. Yeah, I wish I could do that all the time. We had a solder bridge on what is that, U3? We had a solder bridge there and it's gone now.
Oh.
That I think that's pretty good. I'm gonna leave that side alone. It's just a bit of an awkward angle because the microscope, the base of it, the neck of it kind of gets in the way a little bit. Well, I mean, the joints look shiny. It looks like it's wetted. I mean, I don't know. I think we're going to call that a pass. Yeah. There it is. Q6. Let's check out the chat. So we're done with those Qs, those transistors, those MOSFETs. Now we're on to Q8. It's on the top side. So when we look at Q8, we'll see that BC847BPN, it says it's transistor NPN-PNP. So it's a split NPN-PNP transistor. And it looks exactly the same as the part we just did. Hopefully it has some kind of indication of polarity, because in this case, one is NPN, one side's going to be NPN and the other PNP, so that there should be some indication of polarity this time. Like clearer than just nothing other than a couple of marks of text. If I have to look up the schematic, well, we might as well, right? So anyways, we're going to see what most Mousers and DigiKey stock looks like. So for Q8. So there's Q8 there. DigiKey has 32,800. Mouser has 490,000. So there's no shortage of those ones. Let's take a look at the data sheet. Excuse me for a second, folks. Look at that. The print failed. Not sure why. First one did. First one went well. Usually when the printing fails like that, especially on the first few layers, it's a bed leveling issue now. Most printers nowadays have auto bed leveling. Ender 3 is a classic, but it's a workhorse. And it's a suitable production printer, so usually you can set it and forget it. Anyway, a little bit of fun with that. Okay, moving on to Q8 here. And that's just right next to that big electrolytic. Well, polymer. think we're going to take a break in about 5 minutes. Maybe, probably after this part. We went through all that, but we didn't get into the data sheets though. Hundred 45 volt, 100 milliamp, NPN, PNP, general purpose. The important thing to take note here is and it does seem to indicate there's some kind of polarity indicator, so we'll be sure to be looking for that anyways. We use the NPN section of the so this is the MIDI transmit, and this basically just follows up into the output MIDI DIN jack there. Where is it? Yeah, there it is, MIDI TX. And then so it goes through 220 ohm to 5 volts, and MIDI spec indicates that you can just basically drive that with one transistor. You could use a MOSFET or a bipolar junction, it doesn't matter. Anyways, let's put it on there. There's Q8. Wonder Boy in Monsterland. Good Sega game. Good Sega Master System game. Mm. So lucky. Sometimes we lose parts. But we rescue them, you know. It's especially frustrating because the flux makes everything sticky and the parts are especially light. You see, folks, this is why we did the caps first. Our tweezers are giving us a hard time. It seems that the side of the package is not 100% flat. It's going to be a hard one, folks. Well, I don't know where it went. But I guess it's break time. It's break time now. And we're back, folks. Ah, you can see the little orientation mark there. So we weren't having a lot of luck with the other ones, the tongs or whatever, the tweezers. They sure don't make that orientation hole very big. Boy, you'd never see that without the scope. Got the thing too close, I can't see what I'm doing. A little tricky positioning, that one. Yeah, and I feel like it's not right. It's not well positioned. We'll have to try that again. Well, I'm a space cowboy I bet you weren't ready for that. I think that's okay. It's probably a little too much flux. Oh well. Trick is to put just the tiniest amount of solder on your tip. That might be enough. Okay, yeah. Jeez. Let's clean that thing. I think we'll accept that. Yeah. Okay, we're going to shift gears a little bit. We got another set of parts to do. We got 4 parts done. We got 7 to go. So I think we're going to do the crystal Y1 because it lives in the middle of the thing, of the micro. I guess we'll have to do this. Okay. So Y1, we're going to find them. So this is the crystal that runs the microcontroller, 8 megahertz. The pads are on the bottom of the part, which basically means that we have to sort of touch the part on, touch the pads on the side with the blade. And that should just work. You know, like maybe. Anyway. Let's get back to that. What was that? So that's your Y1. Taking a look at BOM on DigiKey with our Y1 here. They got 1,526 in stock. And then on our Mouser Electronics BOM, they don't have the exact same part as as DigiKey, but they have an equivalent that's from a different manufacturer, but it has very similar specs. And it uses slightly different capacitors, which also solves another problem that I had with the Mouser BOM in the first place with the 10 picofarads. So that's basically these ones here. The crystal that they use on Mouser calls for 8 picofarad, whereas the one on DigiKey calls for 10. And so as a result, C64 to 65 on the Mouser BOM uses the proper 8 picofarad caps, whereas on the DigiKey BOM, C6465 uses the 10 picos. And so if you're going to order the 8 megahertz crystal from Mouser, be sure to get the C6465 from Mouser as well, because the parts match. If you get the crystal from DigiKey, get the matching C6465 parts from DigiKey. I mean, because it's just easy, right? Anyways, I guess we could take a look at that data sheet. This part's pretty much the exact same thing as the one that's on the original BOM. It might be a little better. It might be a little better, but bottom line is it's basically compatible. It's completely 100% compatible. Has the same pinout, same dimensions. You know, it's all good. Neato. I don't know why that last print failed, but this one turned out pretty good. Anyway, let's get back to what we're doing there. Yeah. So that's our crystal there going into the pH 0 and pH 1 inputs. You could, in theory, use these as general purpose input-output on the H port if you were just running the thing off of this guy. Or wait, the low-frequency oscillator, this one here. You could technically use these as GPIO if you were just going low frequency. I don't, maybe like it's a watch or something, a portable watch, something extremely low power, and it's like you're not going to use that high-speed port. Anyway, enough stupid bullshit. Let's get to the skinny. There's no actual orientation on this part, even though it's indicated here that there possibly is. Alright, let's pop this guy. It's a little bit tricky. So that's what it looks like on the bottom. The pads don't even go to the side, so we'll have to be mindful. Best tweezers to use is the curved tip, because look what we're doing. Well, I guess there is an orientation, so we'll try and, adhere to that. I guess we gotta tin the pads first. Since we got the blade tip, we'll try to do two. We'll try and do a double whammy. We'll try and get lucky. Might be able to do the Y1 the right side. The blade tip is too big. It's too big. I think we need to rethink this, or shit. We cannot do two at once. It will not work. It won't work. It's not gonna work. Not this way, anyway. Maybe the other way it could have. If I went the other cardinal direction. Wow, that thing just wicked it like nothing. It was not my intention to get solder on the part. I did not realize that the whole thing could just... Okay, so we'll have to get back to that. All right, well, that wasn't fun. we'll fix up the messiness. It's hard to say if that was wetted properly, but we put a lot of flux there. Technically, only 2 of these things have to be hooked up. The other 2 pads are technically not connected, I guess. I guess they don't do anything. It's only we've actually done all the pins that we really need to do. Got that one last one. Which one? That's the first one we did. It's hard to see which one I didn't do, actually. If you're playing along at home, hey, why don't you tell me in the chat? If you're playing along at home, help a brother out. I see. So that's that pad there. That's the one we have to solder. I don't know. I'm being a little bit Mr. Magoo right now. Probably I'm being a little bit Mr. Mick. Mr. Mick, I got flux goo on my fingers. This is such a bad idea. That's better. You know, this is kind of turning into a little bit of a disaster. We could have just left that and, you know, it would have been fine. I'm trying to be thorough, folks, you know? Just remember, folks, I'd be building this on my own the exact same way, and it would be just as frustrating, except I'd be saying a lot more profanity. It's more fun this way. You know, I get to share what I'm doing. I could just added some flux, so I'm gonna just go with that. What did you do? Oh. Like, I don't know if... Oh, man, we probably cooked that frickin' can. No, no, no. We need to clean it. It's a grounded mat, folks, so don't get too uptight about the anti-ESD. So I don't know if that's good or not. We're gonna have to wait until we power up the micro to see if we get, you know, anything. Other than that, and that's the thing, right? Like, so that's the thing with the hidden pads, is that not really sure if it's actually good or not, but I mean, well, anyways, let's just assume it's we'll just have to go with it, right? I tried to get off as much of the solder as I could. But anyways, I think we're gonna have to accept it. The one part looks a little crappy, but oh well. I'm not gonna fuss over a part of it that's not even like, it's just a floating pad. It's not even active. Anyway. Yeah. Okay, let's try something a little easier this time. Folks, we're going to run the stream for 2 hours, and then we're going to call it. And then we'll be back, I guess, tomorrow. So we'll do a little 2-hour stream. We're not going to kill ourselves this time. We'll do 2 hours, and probably we're going to reconvene tomorrow and do another 2. We probably won't get... we got 15 minutes left. That's probably enough time for maybe 1 or 2 more parts. We got this one diode. It's going to be a real pain. It's the smallest diode on the board. It's the smallest part on the board. Anyway, let's take a look at that. So it's D11. It's a diode related to the Texas Instruments chip. The battery charge chip. Okay. So it's a pretty small guy. If there's any part we're gonna lose, this is it. So we're gonna see how it goes. And quickly take a look at the stocks on that. So D11. Schottky diode, 20 volts, 1 amp. Check out the Mouser stock. D11. $79,000. If you look at the Mouser D11 here. 7,300. Pretty simple stuff. It's just a straight up diode, but it's really, really small. And that's it, and it's cheap too. So you can see that it's part of the charge chip circuitry there. It's a Texas Instruments recommended part, and I didn't feel like substituting it for something else, so I just went with it. I didn't like it because there's no bottom pads. You'll see that there is no pads on the side, so it's just like the crystal. There's only pads on the bottom, and, well, we just have to do it the same way. So so what does the diode do? Well, the 5-volt line, the PMID line is 5 volts at all times, or at least the chip tries to maintain it. But this is the switching regulator part. This is the buck booster. And so essentially what it is it prevents any back feed. It prevents the I don't know. You could read the chip. I can't explain it. I've read it a few times, but it has something to do with reverse voltage protection on the other. But you only need it if you want to push 3.1 amps on PMID. So it's just essentially it's a safety thing. But if you're not pushing like 3 amps on the PMID line, you don't really need D11. Just check out the application sheet. The application sheet on the BQ25895M. I don't know. It's not a cheap chip. There's a lot of engineering in it. Anyway, sometimes I talk too much. All right. We'll see how that thing goes. Anyway, moving on. You'll see diode 11 is right next to our huge inductor there that we just saw part of the buck boost circuit. So not as challenging as putting the crystal in and right in the middle of capacitor central there. We've got a lot of playroom here. Yeah, and the strategy here is basically to wet both pads simultaneously while placing the part. And since we don't actually have to worry about pads on the sides, it's nothing to... Yeah, we'll see if we can get lucky. So if you want to have good success with a 3D printer, I suggest you wipe the print bed every time you do a print. Anyway, enough of that. So that's the part we gotta get. We could lose it the microsecond we just open that thing. I mean, it's literally the size of a fingernail. There's my fingernail, that's the part. Watch me stab myself, folks. You know, half the time you spend just opening these things, never mind putting them on the board. Little bugger. Trying to do this on camera to, you know, add some pizzazz. Let's take a look at the chat, see if anyone tuned in. Guess not. I opened the part, folks. I don't know where it went, but I found it. It went all the way over here. Just like that. I didn't want to select these parts, folks. I didn't want to use these parts. Look how tiny this thing is. It sticks to the damn tip because the tip has flux on it. Oh, this is gonna be hard. Come on. It's standing on its side. Yeah, right. I'm going to spend all my time just being able to pick the part up. Never mind. Never mind place it. This won't work. Well, we're going to test for shorts. We're going to test for shorts. Let's clean it up. So, I mean, you know what? I want to test for shorts right now. Oh, but my meter isn't right here. You know what, folks? I think she looks good. I think we got really lucky there. Anyway, luckily that was the only one we had to do like that, and the crystal. Well, we do have the MEMS microphones, but we've got a little sneaky trick for dealing with that one, but we'll see. We'll see how it goes. Anyway, we got one more for the road, and then we're going to call it. Yeah. All right, folks, that's a show. that's a wrap. Thanks for tuning in. If you didn't watch it live, thank you for watching. Please like and share. As always, welcome builders. Thank you for playing along at home. And I guess that's it. We're done for today. So I guess just gonna go to the we're gonna do another live stream tomorrow. Another 2-ish hour. That's all, folks. See you soon.